Welcome to my talk, Using Grok to Walk Like a Duck, which I could have just named the ZOAP 3 component architecture and probably have been less confusing. I'm Brandon Craig Rhodes, a consultant in Atlanta, Georgia, and well, you know where you're at, but the thing on bottom will keep you from getting confused when you look back at it in later years. I'd like to start this talk with a simple question. When you make a simple folder in a simple standard install of Plone, you're actually creating an instance of something called an AT folder, which I think stands for archetypes folder. Does anyone know how many methods an archetypes folder has in order to do all of its archetypes folder business? Yes. Well, I'll give you a hint by listing them on the screen. You saw it when it was minimized? An AT folder, in order to be an AT folder, displays 471 different behaviors, each through a separate method. Both ZOAP 2 and Plone, and that's a symptom of the fact that ZOAP 2 and Plone, built on top of it, solve problems by piling more and more methods on an object as more and more contexts are invented that it needs to interact with. ZOAP 3, which is what I'm talking about today, does something different by using something called adapters. To talk about adapters, I've got to talk for a few minutes about Python programming. For those of you who don't actually sit and program in Python, I apologize for the gibberish that's about to appear, but I and the people in the room who've done at least a bit of Python have got to communicate by way of actual code for me to show you what this means on the ground. Many programming languages use static typing. C, which you've seen if you've ever looked under the hood of the default Python implementation, requires you to declare the type of every variable that goes into a function and every variable that comes back out. This has to be known when you write it. Python is famous, of course, for having dynamic typing instead, where we have no declarations. A function takes some things and returns some things, and you don't know when you write it what those things are going to be. You don't worry about whether an object is of the right type when it's passed to you. In Python, you just try using it, and if it's of an appropriate type, you don't get an exception. This is called duck typing, or well, you might, but ideally you don't. Alex Martelli, I believe, named this duck typing because instead of other languages where we declare the types of our arguments, we just try using it. Does it walk like a duck? Does it quack like a duck? Then we consider it a duck. Or in our example, to make this kind of hit the ground, if whatever in is, a document, whatever, if it's implemented the divides operator and can be divided by 2, whatever that means for it, this function will work, whether this is a number, some kind of string you've invented, or anything else. Now imagine, I'm going to set up a hypothetical example that will drive a bit of the rest of the talk here. Imagine a wonderful duck processing library to which you want to pass an object, but the object that you want to pass isn't a duck. What if it doesn't already quack? What if it bears not the least resemblance to a duck? Here's an example. Imagine that you have a message object from the Python email module. This is really cool. Go home and play with the email module if you've never touched it before. It lets you read in. It has this cool function called message from file. That's one way you can do it. You give it a file with an email message in it. It reads it in, and instead of just giving you back this big blob of text, it interprets the message and turns it into this living object called a message that you can say, is it multi-part? And find out yes. And then actually iterate over the other messages that are inside of it. Because if anyone's ever read the MIME standard, messages are recursive. You also know this if your aunt has ever sent you a forward sent by her mother, sent by her cousin, because through each of those forwards, you know how it gets wrapped deeper and deeper because email messages are recursive. You can have different types of content in them as well in this recursive structure. Well, imagine that you're writing an email browsing, a low-level email browsing system for Plone, and you want to show the parts of each email message in a tree widget. That's the thing over there on the left where you can see that it's getting a single email message and breaking out its constituent parts over there to the left into a tree. you know, it really looks sort of like categories and other categories, but see, at computer science, people like calling those trees, you know, where it starts all closed and you click on the little arrow and it opens the next levels beneath that. You click on the arrow and can open what's in you know, what's inside the inside thing. And drill as far down as you want. You've all seen this on 100 applications and websites. What, hypothetically, if Plone had something called a tree widget that you could hand an object to, and that it would do this cool Ajax-y thing and let a user browse it that way? Let's imagine that the documentation to this tree widget promises to operate on any object so long as it has 3 methods. Name, children to return the tree pieces under it, and then length so that Plone knows how to lay it out with Ajax on the page. And that's our entire task. We've just got to get a message object, which doesn't have these methods natively, and suit it up so that it's able to do these things for the widget. How can we add these behaviors to our message? In other words, how can we make an object which actually isn't a duck behave like one? Any of you old-style object-oriented people might immediately think of subclassing, where you create a new tree message class that inherits from message. That's what it says up at the top line, class tree message, inherits all the normal functionality of a message, but adds what? Those 3 new methods that the tree widget is going to need to display this on our website. As we go through these examples, we're not only going to look at the code, which is pretty clean in that case, but we're going to ask, what does the test suite look like? We're going to ask that because, as others in the community have taught us, untested code is broken code. And if it's not broken now, it will break because you will change it without remembering how it was supposed to behave. Having unit tests to protect you from moving old code off of predictable known behaviors is very important. So we're going to ask, not just is that subclass fun to use, but how easy is it for the test suite to test it? Well, what is our test suite going to do? It's got to instantiate one of these new tree messages we've created and verify its tree-like behavior. Thanks to the simplicity of this wonderful Python class, that's actually pretty easy. You can just get a blob of text that's an email message, run the Python email module message from string function with that text, telling it that we want a tree message, and then just run some assert statements to see if our new message methods are doing what we expect for this particular email message. Now, there were some important reasons that test you just saw was easy to write. We were lucky, first, because it turns out that we can cheaply instantiate messages. In order to create a message, you just need a blob of text. What if we were extending an LDAP server? What if we were extending something that has to have a live database instance up to talk to? Unit tests are simple as long as you're talking to something that just needs some text to turn it on. Testing is much, much more difficult if you have subclassed an LDAP object and have to get a whole LDAP server running just in order to instantiate and test it. That's one way that we were lucky. We were lucky in a second and more subtler way, which is that message from string function that the Python email module gives us, it lets us ask for something besides a normal message, right? Our test suite's not going to get far if all of the things that create messages just return normal messages, because we've written a subclass of message. It's not a normal message that can do the things we need it to. It's this special subclass. Fortunately, the object-oriented gods that wrote the Python standard classes know all about that problem. You run into this all the time, so their functions tend to take a second optional argument that lets you say, email module, turn this text into a message, but don't use a normal message. I need my subclass of message because it's different. So we can actually pass tree message to this function, and it will do its normal behavior, but build one of our things rather than one of Python's normal things. If we were using a library that hadn't thought of that, we'd be sunk. If the library we were calling to get messages back just returned us messages without asking, who cares that we've written a subclass? It is not pretty in Python to get something and dynamically change its class after it's been instantiated and returned to you. And so this is actually not just something that affects testing. This affects your application. If you're using an IMAP library that just gives you message objects without asking if that's what you wanted, subclassing is no help to begin with. A final note. We've actually just broken the message class's behavior. If you look in the library documentation, the len function is already defined for messages. Oddly enough, it means the number of headers in the message. I'm not sure why. I guess because a message is primarily, to them, a container of headers. This means that if you get this message here and instantiate it using the normal message class, the size of the message is 3 headers. Our tree message we just wrote, of course, overrides length because the hypothetical clone widget we're imagining needs length to be the number of my multiparts in the message, and so for this message is 0. If we're creating these messages and handing them to anything besides that little widget, if we just start handing these messages out to normal things that know about messages, they'll break because they'll expect that to be the number of headers. So how does subclassing kind of stack up? Well, no harm to the base class. If there's any other parts of this huge clone app which just need to create, use, and then destroy normal messages, they still behave the same way. But we can't write unit tests in isolation of all of the complexity of the message class. We need to be in control both in the app and during testing of the factory returning us message objects, or else we can't use our subclass to begin with, so it'll only work sometimes. And finally, this breaks if new features we need to give a message for operating in this new environment have the same name, like __ length, as old functionality that a message was already depending on. So with 3 strikes against it, knocking it down 3 letter grades, I think we can only really give subclassing a D as being a general way of adding new functionality to an object to get it to behave in a new environment. Second thing, some of you who have used mixins immediately think, but wait a minute, instead of just creating a single subclass and adding in right there our new 3 methods, well, what if we created a mixin that just inherits from object, it's not special at all, that implements those 3 methods, and then create our special tree message subclass through multiple inheritance from Python's message and our little mixin? And the answer is that this actually helps a lot. Our test suite can now decouple itself from all of the potentially very expensive behaviors of a message. Again, doesn't matter that much for a message, but it does if it's an LDAP server connection you're trying to subclass or improve. Because the test suite can do this. It can create just a fake message that inherits from our mixin and gets our 3 new behaviors that mocks up fake versions of the things a message does, like return its content type, creates an instance of the fake message and then can test whether our methods are giving the right behavior given the fake values that this is returning. This is a huge thing to know about doing if you are subclassing or improving something like a database connection, where you don't want to have to set up a database just to run your user tests. You want to be able to run against a fake object that acts for the sake of the test like it's grabbing database data, but actually isn't. How does a mixin rate? Again, no harm to the base class. You can now test the mixins methods by themselves, separate from all the rest of the complexity of the inherited class. So we only keep those 2 last strikes against this method, and we actually move up to a passing grade. With a mixin, subclassing earns a C grade. It just barely passes. It's only for the sake of completeness that I'm going to mention monkey patching. Monkey patching means that you load in another Python module and then change it. For every other user of a message, you create these 3 new methods, and to do it correctly, you actually need something a bit fancier than this that doesn't fit on a slide. But this gives you the idea. You create the methods and then go stick them on Python's message after you've imported that module, and you overwrite things that the normal Python code of the message class inserted. Is this desirable? Well, we don't anymore, if we're monkey patching, care about factories. Huh, because we don't need some special kind of message. We've gone in and overwrote the necessary parts of a normal message so that it now carries the behaviors that will let it display in this widget. But we've changed the class itself so that if other parts of our framework were counting on just creating normal old-fashioned messages and using them, those other parts of the framework that maybe someone else on our team is working on are going to break for very mysterious reasons when our part of the code is activated in ways that are very difficult to debug. It still gets broken by collisions because if messages length and what we need length to do are different, only one of them can win. Whereas you can make many subclasses of a class, and it's fully extensible. You can subclass something 10 times, and the subclasses don't interfere with each other. You can pretty much monkey patch something once. When second and third and fourth monkey patches come in and touch a class, it tends to break because they fight each other. And finally, Ruby people do this. So with 4 hits against it, monkey patching gets an F. So thank you for being patient through the kind of object-oriented theory setup to what the answer to this is. And this isn't my answer. This is an answer that was come up with more than a decade ago by people who had much larger problems than we have because they worked in C++. The famous Gang of 4, because it had 4 authors that no one wanted to remember the names, the famous Gang of 4 design patterns book revolutionized object-oriented programming in 1994. Adapters and what the other things I'm about to talk about are kind of one of the foundational aspects of object-oriented programming. They're actually completely necessary in Java, because in Java, if you have a class that's a message and you're passing it to someone who wasn't expecting a message, you're sunk because it's going to check the type and reject your attempt to pass it. So what I'm about to talk about is actually necessary in Java, and my Java friends do adapters day in and day out just to get their code written. But the idea is this. The idea is give up. Quit. Stop trying to make the message do things it's not built to do. Just relax. Quit. Accept the shape of the universe. And write your own dang class. Write something, we'll call it a message-to-tree adapter, that has those 3 methods on it and that asks a whole separate message object you've given it for the back-end information it needs to construct those answers. Here is a working example of an adapter. Notice it doesn't inherit from anything special. There's no import statements here. This is not, to write adapters, you don't need a framework. You don't need anything but plain Python. It's just a way of organizing your code and thinking about it. In order to have an adapter, we have, as you can see here, we have our 3 methods looking very much like they did when we were subclassing. But we have an init method, because note, this is the first thing we've written that has to stand alone as its own kind of object. We have an init method that when you create a message tree adapter, you give it a message. Watch carefully. It gets the message and puts it behind its back. This is very clever, because when you come along later and ask for the name of this tree node or its children or its length, it's kept that message object you gave it as an instance variable. And it can say, my name? You want to know my name? And then it will surreptitiously look behind its back. And it will come back out and be able to give you the correct name because it's kept a reference to the message that it's wrapping up and suiting up to display different than its native behavior. So in your code, how do you use one of these adapters? Well, you call your IMAP library and it returns a message object, and that's not what this cool little tree widget wants. So you remember, it's going to break if we just pass the message right to the tree widget. We instead instantiate the tree widget by getting the message, wrapping it in the message tree adapter. You see right there, I'm passing it to that init method you just saw that's going to save it behind this other object. And then all the tree widget sees is the message tree adapter. It never sees the native message behaviors that are wrong in that context. It just sees the tree behaviors, which are the correct ones. How does testing look? It actually winds up really simple because notice my adapter didn't check the type of the argument it was sent. I mean, it doesn't know if it's really a message that you send it as that argument to the init function. So you can just, in your test suite, if messages are very expensive to create, you can just create a fake message that gives some, pat answers to content type and stuff, pass that to a message tree adapter, and see if the right answers come back. The adapter design pattern is very powerful. You don't wind up harming the base class. Messages still act like messages, and other parts of your framework that use messages aren't going to randomly break because you've done this. You can test with a mock-up instead of the real class if it's expensive to create. You don't need to control any factories. If your IMAP library just returns messages without asking if they need to be some special subclass, that's okay because your adapter is designed to work with a normal message. It doesn't need to be changed. The changes come externally to the class. You don't worry about collisions. This is the first solution we've looked at today where it doesn't matter that the adapter's length is going to say 0 for that message we looked at earlier, but the message thinks its length is 3. For the first time, we've decoupled its behavior in the new environment, where length means one thing, from its behavior in the old environment. For the first time, we don't worry about that. The only problem is that having to remember to wrap it before passing it everywhere is really annoying. But it solved all of our other problems, so with only one hit against it, I'm going to give it a B. It only gets knocked down 1 letter grade. Now, why did I call wrapping annoying? I mean, my example, admittedly, made it look very easy. You get the object that can't be digested by a tree widget, you wrap it in the adapter, and you pass it on, and it works. Well, the example looks easy, because there I was only doing it once. But in a real application, it's going to happen all through your code. Imagine that you have object producers on the left, IMAP libraries, databases where you store messages. You're getting these messages and handing them to things on the web, to widgets on your Plone site, maybe to an interactive GUI you're writing, where they need to have somewhat different behaviors to be displayed. Well, sometimes you're going to have to wrap it in adapter A, sometimes in adapter B, sometimes C. As you can see on the upper left, sometimes you forget, oh, how do I adapt this? And then you remember you're passing it to someone that actually knows about a message, so it doesn't need to be wrapped at all. And that gets, all that information gets scattered through your code in a lot of places. It makes you repeat yourself, and it also locks you into using the particular adapter you've written with. If you wrote little adapter A and then call it 10 times in your code, what happens when you find out that Kapil has written like this much fancier with caching adapter for turning messages into trees, and you give up and you just want to use it instead? You've got to hunt through your code for everywhere you called the other adapter and make sure you change the import statement and change the code. How could we avoid that? How can we avoid repeating ourselves and scattering information about adapters and consumers everywhere? Let's zero in on the adaptation step itself and ask this magic question: why does it work? Why is the tree widget happy with this statement? The key is seeing that two completely separate issues or pieces of information are conflated inside of this one line of code. The line works because a tree widget has a need that our adapter happens to meet. But if we just manually in our code write statements like this everywhere, which by the way is what Java people do, at this point in the talk, we're done with the adapter design pattern, and we're talking about the new exciting dynamic behavior that we Python people get that nobody else does. So we are moving beyond what OO people in Java are in general able to do today. If we call the adapter, then the fact that there's a mapping here between a need and a want stays hidden inside of our head. We need some way to define what a tree widget needs that the adapter provides. The answer to that is the concept of an interface. Again, this is from design patterns, and they do use these in Java, though not dynamically, as I'll talk about in a minute. Java was actually based on a very cool systems language called Modula 3. Read the Modula 3 report some evening if you need to sleep. I actually thought it was really cool. They came up with a lot of these ideas. And adapters have been brought to Python. There have been several people that have written implementations, but I'd say the best implementation going is ours, is Zope 3. For the moment, let's forget Zope, the big web framework, and just look at Zope.interface and Zope.component that with 3 simple steps will put adapters around classes for you and rid your code of the need to do manual adaptation if you follow that design pattern. 3 simple steps. We're going to define this thing that I haven't defined yet called an interface, register an adapter for it, and then the consumer needs to request adaptation. Guys, this is working Python code. You can go home, look up this talk or my slides on the web, and this will actually work. We always start interfaces with a capital I. This is a convention that goes back to the Gang of 4 so that we don't get confused in our code between what's a class and what's an interface, since they both start with capital letters. But the idea here is that we create a tree interface, which from here on out I will call iTree, that defines that, well, to be a tree, you need to have a name, you need a way to return 0 or more children, and you need a length. And then, there's several ways to do this, but the easiest way is just to kind of manually call provide adapter. We're going to import Zope component, which keeps up with adapters, and tell it, hey, we have a message tree adapter, and it's this really cool thing that takes a Python email message and makes it behave like iTree, like that interface specifies. Finally, in the tree widget, all it needs to do when it receives an argument is request that the argument be adapted to the iTree behavior. Now you're going to look at this and frown and say, that looks really weird, Brandon. You're calling this new thing I hadn't even seen until a minute ago called an interface. You're calling it like a function. That's weird, Brandon. Why would you call an interface like a function? What happens when you call an interface as a function is that Zope.component wakes up and says, ooh, someone needs this arg variable to act like a tree. What is its type, and has anybody registered an adapter yet that tells me how to get this type and turn it into something that behaves like a tree? And if it finds an adapter, it will do that wrapping call by passing arg as the first argument to your descriptor's instantiator, and then return the adapter for you. And this is neat, because in doing this, Zope becomes Pythonic. You do this all the time. When you need something to behave like an integer, you wrap it in int, and you get out a perhaps different object that behaves like an integer, right? When you need something to act like a list, you wrap it in list. Same with a float. You do this all the time. You get a type, and you call it like a function in order to turn an object into that kind of type. That's exactly what's happening here. We're getting an argument and saying we need this to behave like a tree. And that's it. That code I just showed you is working code that will actually work. This is a fundamental way to get code people are writing plugged into applications, define an interface, register an adapter, and then every consumer has to just ask as it gets an object, hey, can you turn this into the sort of thing that I need? Above and beyond the advantages we already saw to adapters, dynamic Zope adapters mean that we don't have to call them. They get centrally registered, and every consumer that needs that behavior gets it automatically without us having to remember who can handle messages and who needs them to behave a bit differently. And I would argue it's with dynamic adaptation that this object-oriented innovation, which is about, 15 years old at this point, moves from a B grade to an A grade and to a really awesome solution. What this does is the information in your code, if you're calling adapters manually about what adapters provide, gets pulled up into your adapter registrations. The information about what consumers need, I need it to act like a tree, I need it to act like whatever, gets pulled over to your consumers, and adaptation disappears from your code because the information about what adapters do and what customers need is now in the adapters and on the customers where it needs to be. Finally, I'm going to talk for a brief moment about what it looks like to adapt an object for the web. Dum, 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 bum, 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 bum. And so this is the friendly caveman, Grok. Grok is a very friendly caveman with a very large club. It's a web framework built atop the ZOAP 3 component architecture that makes ZOAP 3 simple to use and to present. So rather here, as I finish up, rather than give you native ZOAP 3 adapters, which involve some XML, I'm going to write them using grok, which lets me just do it in Python code. Imagine a person class, someone else wrote it, full of business logic that you don't want to touch, and you want to browse person objects on the web. What might an object need to do to be on the web? I would suggest three things. A URL that comes in needs to be able to go find, oh, when you look at personapp/Joe, you're looking at this particular person object. Second, you need to return to the web browser an HTML document that gets the information out of the person and formats it up so that it can be seen. Finally, the person object needs to know its URL so that if you do a search that returns 10 people, you can turn Joe and Julie and everyone else into a URL to link to them. I'm going to show you working grok code that does that for a person object that knows nothing about the web. What's at this URL? You have to know how ZOAP 3 processes a URL in pieces. Each little piece is called a traversal. It goes through each thing delimited by slashes. So what it's going to do is it's going to start at the root object of your ZODB. It's going to adapt that object to iTraverser and call the magic traverse method that it now gains or as a result of that adaptation and say, hey, we need to go inside of you, root object, to whatever you call person app. And then it's going to get the person app object and say, hey, is there something inside of you called Joe? Just like a file system asking a bunch of directories, hey, do you have this next file name inside of it? In order to give the object the ability to do this, we can create a traverser, look at this code in detail later, but these 6 lines, are a full-fledged grok traverser that say, hey, if a person app is asked for a name, go to my database calls, see if there's a person with that name, and return them. The second step, rendering them as HTML, in grok you do it as a combination of a little bit of Python and then a page template. It auto-associates them based on the lower classing the name of the class and putting .pt at the end. 3 lines of code, you can have a default, that's why I named it index, view on a person that gets this object that can't be delivered to a web browser and turns it into HTML that can. Finally, what is the URL? You can inspect this code later. I thought it was a bit ugly, but it was the best I could do in a hurry. Because again, ZOAP uses adaptation to answer the question, what URL does Joe live at? It adapts Joe to the IAbsoluteURL interface. So if you write something that can take these person objects ZOAP has never heard of and adapt them to absolute URL, you can return what URLs things need to have to be displayed, and it'll work automatically. So 6 lines in order to get it discovered at a URL, 3 lines of Python to get the page template hooked up, and then it took me 8 lines to give person objects a URL they can spit back. With 17 lines of code, I have managed to suit an object up for the web without touching it, without changing it, without altering it at all. The object has not been harmed in this process. It has gained new functionality by being surrounded by a little cocoon of adapters that answer questions on its behalf when it needs to be shown to the web. If you look through ZOAP 3, you'll find that it uses adapters for all sorts of things. You can put adapters on your objects to make them appear in menus, put adapters on them to make them secure, put adapters on them to internationalize them, all sorts of things. I'm going to finish by pointing to an excellent example of this that there was a presentation on yesterday, which is Vice, the new Plone RSS and Atom feed engine that Paul, is Bugney or is it Boonyi? Does anyone know how that's pronounced? Huh?
The second one.
Okay, cool. Bugni? Or something like
It's
that?
supposed to be Italian, it's Bugni. But
Bugni? Okay. He presented on that, he presented on this just yesterday. Think about an RSS stream, guys. What has an object got to have happen to it? Well, if all of the properties the object has, one of them has to be chosen and reformatted because of RSS's character code limitations and stuff. You have to pick something out to be the title, pick something out to be the short description, pick something out to be the long description, pick something out to be the last modified date. You've got to go grab a bunch of stuff off of it. The old-fashioned way to do this would have been to go to a bunch of objects and add, this is how we get 400 and 500 methods on an object, is whenever a new need comes along, you go and make it more and more and more complicated to be able to exhibit the proper behaviors in these new contexts. But the Vice people have built this new RSS subsystem on top of ZOAP 3 registered adapters. So the way it gives content objects RSS superpowers, so they can appear in an RSS feed, those same three steps: define an interface, which they called, I think, iFeed item, register some adapters, and then before they display an item in RSS, they just ask for it to be adapted. And if you go look at their code, go check out plone.outbound.vice, you can actually find in their code a series of adapters that they set up and register to get a document, a Plone event, a Plone link, an image, a file. And there are these thin little classes that just grab the information off of the document, reformat it and encode it, and present it as a series of little attributes ready to be absorbed by the RSS subsystem. They have added something like a dozen methods to 6 different objects without making them any bigger. If you load plone.vice, these new adapters and capabilities appear for the objects. If you later kick it out of your site, they disappear. The object itself gains no more methods and becomes no more complicated than if Vice were not present. One last thing, adapters can be local. So if you're using them for skinning or theming, as ZOAP 3 goes down the URL, and hopefully soon, they might have done this, I don't know if they've done this with Plone. You guys call this placeful, where certain facilities are only available within a part of your site. Adapters can work exactly the same way, where as you go deeper, some new adapters become available and old ones can even get overridden, so that only in a certain folder or subsection of your site is an adapter available to make something RSS visible. The rest of the site, those objects can be hidden and safe. Go ask Leonard or Martin about 5.grok. I heard a rumor that in his tutorial on Tuesday, Martin says that he actually is now writing grok code like I showed you before, and it's making objects work inside of his Plone site. Thank you very much. When you come back to the slides, here's some links that you can follow. I think we're out of time for questions, but if you have anything you want to ask, just come on up.